Since the earliest days of spaceflight, rocket technology has relied on standard combustion, a chemical process known as deflagration. Even as these early rockets evolved into massive modern spacecraft, the underlying chemistry remained the same. This illustrates the core engineering problem. Continuous combustion engines have reached a hard thermodynamic efficiency ceiling. No amount of clever engineering can push past this physical limit. Hitting a hard physics limit meant the aerospace industry could no longer rely on incremental tweaks. They had to search for a different approach to propulsion. For decades, aerospace engineers chased a theoretical concept known as the Rotating Detonation Rocket Engine, or RDRE. Instead of burning fuel, it creates continuous, spinning, supersonic detonation waves inside a circular chamber. This creates immense pressure and extreme heat. For a long time, placing this process inside an engine simply fractured and melted the materials used to build it. To keep the engine intact, engineers needed complex internal coolant structures. Traditional subtractive machining, using drills and mills to carve away metal, physically could not reach inside the walls to create those intricate pathways. The physics of detonation were understood for nearly a century, but 20th century tools provided no path to actually fabricate the complex hardware required to manage the energy. That manufacturing roadblock began to clear with Houston-based Venus Aerospace, a startup that recently closed a $91 million Series B funding round to build and scale a working RDRE. The shift that made their design possible is additive manufacturing, specifically laser powder bed fusion, where a high-powered laser melts microlayers of metal powder to build complex shapes from the ground up. This cross-section shows what 3D printing enables, an intricate network of microchannels built directly into the engine wall, routing liquid coolant. To survive this environment, the process incorporates GRCRP42, a specialized NASA copper alloy chosen for its high thermal conductivity, transferring and dispersing extreme heat. Engineers then added a second NASA alloy, GRX810, which provides the temperature resilience required to withstand the physical impact of a supersonic blast wave. By combining laser powder bed fusion with modern superalloys, Venus Aerospace took the RDRE from a theoretical paper concept and forged it into physical reality. These theories faced validation during a May 2025 flight test at Spaceport America in New Mexico. The high-thrust engine successfully launched, flew, and maintained complete system integrity under real flight conditions. This bar chart displays the critical metric, comparing the historical plateau of standard combustion engines against the 15% efficiency increase achieved by the RDRE. This gain translates into extended ranges and payload flexibility, carrying heavier cargo to a higher orbit on the same propellant. This successful flight test makes the RDRE the most efficient rocket engine architecture ever flown. Rather than engineering a unique engine for every single application, Venus Aerospace is building a common, flexible propulsion architecture. This single architecture is designed to serve mission classes ranging from munitions and space launches to orbital transfers and landers. Historically, aerospace platforms have suffered from a reliance on constrained, foreign-sourced parts distributed across fragile global supply chains. Relying on these 3D printed components eliminates that vulnerability, allowing for domestic manufacturing at scale contained entirely within Texas. As highlighted by investors like Lockheed Martin Ventures, the ultimate value of the RDRE lies in its operational advantage, the ability to produce a high-performing engine on a fast, reliable, and trusted domestic supply chain. It took a century to move from an unbuildable physics theory to a deployable, high-efficiency engine. The recent $91 million in capital is intended to scale the physical production of these printed engines for defense and commercial space programs. Additive manufacturing bypassed the constraints of legacy machining, providing a way to build geometries that drills and mills could never reach. The barrier to higher efficiency wasn't a lack of scientific theory, but a lack of manufacturing precision. With additive printing, we can finally build the hardware our predecessors could only model on paper.